Okay, so now we'll say something on, I will start saying something about mirror symmetry to go like towards the explanation for why this conjecture should hold in general, or how do we actually prove it in dimension 2. So as we discussed, even this example, even this historic example from the B side is maybe not clear, like why, like, okay, if you forget that you have this toric monomial, it's unclear why the kind of B side moduli space has this decomposition, for example, or why does it contain a torus? It's unclear in general. And in addition, it should be toric, so there should be some kind of fan which describes the compactification of this moduli space, and understanding this boundary is unclear from the B side. And the general idea is that from the A side, there will be some kind of natural fans coming out just from birational geometry, just Keller cones of the mirror. And so you might worry that this thing is also not so good. Like maybe you should think about compact Calabi-Yau. Keller cones of compact Calabi-Yau can be very bad. They have no reason to be polyhedral. It can be complicated. But here the point would be the mirrors of this kind of non-compact Calabi-Yau will be like simple from the birational geometry point of view. So the claim will be that they will always look like that. So in the toric situation, the mirror is like X, some Crépont resolution of a affine variety with canonical singularity. So this thing will be the expectation. So the expectation, which should hold in any dimension, is that if I start with one of these log Calabi-Yau with some line bundle, so y of dimension d, then I should have some mirror, which I denote by x bar. We should have a map to, okay, here let me say something not fully correct, but let me say first map to C. And this thing should be some, let me say, affine d plus 1 dimensional Calabi-Yau, and with canonical singularity.
So affine, you expect affine because D has the zero-dimensional.
Yeah, that's how I think it's a reason. Exactly. When D, for example, if D is smooth, then this thing will, for example, in dimension 2, if D is an elliptic curve, then in the mirrors, this x bar will contain some mirror families of elliptic curve, and it will not be affine. So you expect this affine only in this kind of maximal log Calabi-Yau situation. And then it's a general fact in birational geometry, which says, so this is result in essentially MMP. And in any dimension, it's more or less written in the paper of Birkar, Caccini, Icahn, McKenna, which realized a big part of the MMP in all dimension. So they prove many, many things, but one of the corollary of what they prove is the fact that if you have a canonical singularities, then out of it you can construct a Mori fan, which is really some complete polyhedral fan. So really nothing fancy. There is be a vector space. So where is this fan living? So it is a fan in like the relative H2 or relative Picard group, whereby X is the Crépont resolution. So here there is a technical point which will be relevant later, which is in any dimension a canonical singularity might not admit a smooth Crépont resolution. By birational geometry, the best you can think is to find a resolution with so-called Q factorial. Terminal singularity. It's something, okay, it's again some digression. It's something which is already true in toric geometry. If you start to look at toric geometry in dimension 3 or higher, if you take a polytope, it's not always possible to triangulate it into simplices, into standard simplices. And by standard simplices, I really mean the standard simplices of integral size 1. So I claim there are 3-dimensional lattice polytopes. I will not be able to draw them. there are three-dimensional lattice polytope, which are combinatorially a simplex. Which do not contain any other integral points apart from these four vertices, but still is not it's not the standard lattice simplex. So this thing, because there is no other integral points, you cannot subdivide further. And this thing is an example of Q factorial terminal. So this thing exists even in the toric situation. But yeah, let me forget about that. So okay, let's pretend there is Crepont resolutions. Then the claim is that there are really finitely many Crepont resolutions, and for each of them there is some version of the Keller cone, which is really a polyhedral, finite polyhedral cone. So it really looks like the fan of a. So there are finitely many cones corresponding to the various Crepont resolutions. And then as in the toric situation, when you go to the boundary of this union of cones, you get this divisible contraction. And there is always a recipe to complete like lower dimensional cones into higher dimensional cones to get some kind of complete pictures. So in birational geometry, this thing is, having this property is more or less being a Morey dream space. So this space is like some kind of relative Morey dream space. There's a space which are like dreamlike from Morey property. The naive cones are just polyhedral, and there are finitely many of them, and they all fit together. So this thing gives you a natural like source of fans, like on the A side. Like if the mirror is like that, then just the birational geometry of resolution gives you a fan. And so this fan and the kind of the toric variety associated to this fan is a natural candidate for a kind of compactified, extended Keller moduli space. And so you might believe that this toric variety should be the compactified B model on the other side. So if you can't find a mirror like that, at least you have a candidate for the toric variety which appear in the conjecture. So now there is two things. So if you want to prove the conjecture, there are two main things. The first thing is, can you construct the mirror? And once you get a mirror, can you actually prove that this thing is the correct answer? Can you prove mirror symmetry? Can you prove that this version of the Keller moduli actually agree with the B model moduli space we're after? So can we construct the mirror? Is maybe the first question. So I think it's fair to say that in complete generality, okay, the point is that in complete generality we can, okay, so how do we construct the mirror? Okay, so here, okay, so if it were toric, there will be some toric mirror symmetry, which is some combinatorial duality. But if we start with a random maximal log Calabi-Yau pair, how can you get the mirror? So the only construction I know is this intrinsic mirror symmetry. So this intrinsic mirror symmetry of Gross and Zibert is something very general. And it can take as input something like that, an arbitrary log Calabi-Yau pair. Again, I'm skipping a few technical details, but roughly you can take any log Calabi-Yau pair like that with an ample line bundle. And it will produce for you a mirror, X bar. And let me try to explain. So I guess Julia last time gave examples of mirror construction. Let me give a few words about what this intrinsic mirror construction looks like. And it's particularly relevant for my story because at the end we'll do mirror symmetry twice. So we'll actually try to apply that twice. And I want to make some comment about going back and forth. So we start with a log Calabi-Yau YD with some ample line bundle L. And okay, so what is the intrinsic mirror symmetry recipe to find a mirror? First of all, you look at the dual intersection complex of your log Calabi-Yau. So it's some kind of union of cones, like the tropicalization of this pair. And you look and see things as each of these cones has a natural integral structure. So you get this collection of integral points. So if you are starting with something toric, it would just be the fan in the integral points in the fan. And then the way, so in this case, you expect the mirror to be affine because it's maximal, this tropicalization has maximal dimension. So you expect the mirror to be affine, so you will just write spec or some algebra, and so you just have to write to find out what is this algebra. And the intrinsic mirror recipe is the intrinsic mirror construction is a like recipe to write down an algebra. And the recipe is to write down an algebra which has a vector space contain a basis element theta p for every integral point in this picture. So p is an integral point in this picture. And this algebra will be an algebra over some ring so any of y is a monoid of curved classes. So concretely, an element here is some kind of power series of the form C beta. And actually, OK, let me modify that. Here, I have actually a line bundle, which will simplify my life. I don't want to produce a big mirror family. I only want to produce something living over C. So actually, it will be over C double parenthesis T. It will be much simpler. So this thing will live over, OK, and in the general construction, I only give you something formal. So I will not be able to produce for you like family over C, but I will produce some kind of formal neighborhood of some kind of central fiber, which will be kind of good enough for many purposes. We can do this result in birational geometry. They work for formal things. It's fine. So here is a vector space. For each integral point, you write a basis element. And the whole point is to know what is a product on this algebra. And the intrinsic mirror symmetry recipe is to say that the product, so the product of two basis elements is supposed to be a linear combination of a basis element. So I want to know what are the structure constant. And the point is that the structure constant will be the sum over R. The structure constant will be curve counts. CPQR beta T to the L dot beta. Where CPQR beta is a count of like rational curves in Y really relatively to D. So these are really defined using log Gromov-Witten theory as sketched by Julia the first day of class beta. So for people who never saw this definition, something much more familiar is quantum cohomology. You define a product by counting holomorphic spheres with 3 contact points. And this definition is kind of analog. You also count rational curves with 3 mark points, except it's not inside a compact variety as for standard quantum cohomology, but it is inside a variety equipped with a divisor. And so at the contact point, you can have non-trivial tendency conditions along the divisor. So I will not go into the details of the definition. It's where all the difficulty is. We need to develop log Gromov-Witten theory to define these numbers. And the amazing thing, which is the same amazing thing which happened for quantum cohomology, is that you get some associative algebra. And the kind of deep reason for it is the same as in usual quantum cohomology. You have this moduli space with curve with 4 points, which degenerates in 2 different ways to union of moduli space with 3 points. And so the theorem of Gross and Siebert is that there is a way to define a product like that, and this thing defines you a commutative associative algebra. So this thing is an intrinsic mirror. It takes as input these rational curves. And if you prefer to think of mirror symmetry in some kind of maybe SYZ way, this curve, you should think about it as having something to do with like quantum corrections, holomorphic curves with a boundary on the XYZ fibers, which are related to the existence of singular fibers. Okay, so there will be a very long story to how to go from the XYZ heuristic picture to this number, but it's not so surprising that at the end of the day you have some kind of modulus of your mirror is a modulus of Lagrangians, which is corrected by some kind of curve. So it's not so surprising that something like counting curves should be involved in the construction of the mirror.
If you have more than one zero-dimensional straight line,
yes.
so each of them you should expect to have a torus nearby, right?
Yes, that's
all the same.
Yeah. So I think there is. I was thinking that there was a statement proven like that, but okay, the last time I tried to find, I could not find the reference, but I'm pretty sure that under quite general assumption that is known to be true.
Is known to be true?
Okay, my vague memory is that it is known to be true, but the last time I looked for a reference, I could not find it. but yeah.
So the claim is that if you have two maximum,
but then we are getting the same formula.
Yeah, and somehow it should be true, like for this picture to even make sense, because in complete generality, if you can have Calabi-Yau's, which are like very two different XYZ fibrations, which have nothing to do with each other. And for example, the mirror do not even have to be birational. They might not be related by flop or something. But here there is some kind of preferred XYZ fibration, which is kind of why they're all related by flops. Like there is not like exotic.
Well, because the definition of C never use.
Yeah, that's right. Yeah, that's right, exactly. It's clear here there is nothing. No choice. Yeah, exactly. Yeah, so.
Oh, I see, because that point is the same for all points.
Okay, so at least you have a candidate for X bar. And I think this thing works in dimension. You can write this X bar. I think the thing which is not known, I don't know how to prove that X bar has canonical singularities in dimension 3 or more. I think, so for D, because it will be the kind of general theme of intrinsic mirror symmetry. You can define something, but it's defined using curve counts, and then to get any like concrete algebra geometric properties of this space just from kind of the structure constant of the algebra is something not trivial at all. So it's related to the claim that, if you think of this X bar as some kind of family, so there should be some X0, some central fiber, which is really easy to understand. And then this thing should be some one parameter family. And this one parameter family should be some kind of smoothing. Like, so here there is always X0 bar, which is really easy to understand. X0 bar is always a union of toric thing corresponding to this code. So X0 bar is really easy. But then you deform it. And I think to prove that, the kind of thing we need to prove is that, okay, if you forget it's formal, if it's really some honest family, you would like to prove that the general fiber is like irreducible. Like this union of things just become a single thing. At least you would like to have that. But I think I don't know how to prove that, starting from D bigger goes than 3. Because just using this definition, how do you see that
but
this?
It should be true, or is it not obvious? This may not be true.
I think, okay, the optimistic expectation is that it should be true. But in complete generality, I don't know how to prove it. So definitely there are examples in higher dimensions for which we could prove it by indirect ways, but I don't know some kind of like a priori ways to prove it. Yeah. And so in dimension 2, this thing is true. It follows, it's already sees X bar as being studied by Grossack and Kill in the work on mirror symmetry for Calabi-Yau surfaces. So that's good. Which means there is some X bar, which means there is a candidate fan. Okay, so that's good. So you get this Mori fan which is our candidate fan, and I will denote by T the corresponding toric variety.
So is that the only place you use the equal to?
Okay, we'll use the equal to in many other places, but it's the first place. Okay, so we have a candidate toric variety, but the whole issue is so we have a mirror, but now the whole point is to prove mirror symmetry. So this thing by construction is an A model moduli space, but now we need to show that this A model moduli space is a B moduli space that we defined at the beginning. So what we want, we call it a map from this toric variety to our B model moduli space. So to get that, so we want to show that the A model moduli space is a B model moduli space, so we need to construct a universal family of Y, D, and L over this moduli space. So to do that, we want to construct some kind of universal family. And actually, so we really want, so the object we parameterize in this moduli space was this pair, Y, D plus epsilon C. So you have to construct a family of Y, you have to construct a family of D's, and you have to construct a family of C, such that these pairs are KSBS stable, that C avoids the zero-dimensional strata and so on. You need to construct all that over this toric variety. Okay, so if you can construct such families, then by universal property, you get a map to the moduli space. And if you are lucky, maybe this map is almost an isomorphism. Maybe it's a finite map.
Oh, that's a different C.
Oh yeah, I think my calligraphy is not. This thing is supposed to be a C. This thing is supposed to be a T. I think from my. So maybe it's supposed to be a T, like toric, maybe something. Okay. So remark that in the first step of the story, I wanted to find the mirror. So I was thinking of YD as being the A side. Like I was counting curve in YD. Then using this count, you produce the mirror X bar, which is realized as some kind of B side. But now what you want is to find the mirror back. So now we want to view a C side as an A side and find this family as being the B side. And so you might think, okay, let's start here and let's try to find the mirror. And you might say, okay, let's apply intrinsic mirror symmetry. But it does not work because this thing is not of the same nature. It's not really the kind of thing we started with. Like the thing we started with was a kind of nice log Calabi-Yau, like a variety with some normal crossing like divisor. But this thing is a badly singular space. In particular, you cannot do, or at least it's not known in any reasonable way, how to do Gromov-Witten theory or log Gromov-Witten theory of such a space. So definitely you cannot directly apply and somehow it's expected because if you want to do mirror symmetry, you should be near the large volume limit on the A side to find a geometric mirror on the B side. Okay. And so you should go to the large volume limit, which means you should look at crepant resolutions. So you cannot consider X bar, instead look at X over X bar crepant resolution. And so already here there is many things which are unclear. So X bar, in general, the fiber of the zero looks something like that. And then so we are looking for some kind of crepant resolution. But then if we want to apply, okay, so here it's a slightly different setting for intrinsic mirror symmetry. It's not a priori a fixed. Maybe this thing a priori does not look like a fixed variety with a divisor, but actually it does. So here the right divisor to consider is a central fiber, so X0. So I really have a pair, which is a total space X, and the central fiber X0. And if I want to apply intrinsic mirror symmetry to this pair, I would like to know that X0, so if I do this Crepont resolution, I will need to know that this X0 is a normal crossing divisor inside X. And this thing is not guaranteed by general birational geometry. So maybe this thing will have a Crepont resolution, but there is no guarantee that this central fiber sitting inside the total space is normal crossing. But there is a miracle that, so in dimension 2, so it's definitely a place where you use dimension 2, we kind of give an explicit construction of these X and X0. And actually, this construction is something I sketched at the very end of my very first lecture. This explicit construction only uses some. Okay, so here it crucially uses the fact we're in dimension 2. And it crucially uses the fact that any log Calabi-Yau surface in dimension 2 with the maximal admits a so-called toric model, meaning it can be obtained by starting with something toric, then picking some points on the boundary, then doing some blow up, and maybe doing some also toric blow up and blow down. So there is some kind of, so this thing uses geometry, birational geometry of surfaces, which implies that all these maximal like Calabi-Yau, they are all rational in particular, and they are kind of all connected to toric surfaces by kind of understood birational blow-ups. So they are not toric blobs, so this thing really go outside the toric words, but it's kind of connected to toric geometry by some kind of known birational transformations. Which means that this mirror we are looking for is kind of connected to some toric mirror symmetry by some kind of deformation. And doing some deformation theory, we can explicitly produce this X. So actually, we can produce this X and this X bar actually without using intrinsic mirror symmetry. And actually, in our paper, where you prove our conjecture, actually we don't prove that the mirror we construct is the same as the one you will get by running intrinsic mirror symmetry, but it's something which should appear in some future later paper.
Okay, so we use intrinsic mirror symmetry.
So for this step, in what we really use, we don't use intrinsic mirror symmetry to this step to produce this X. We kind of produce a Crepont resolution X by describing explicit irreducible components we glue together. And we argue there is a way to contract to get some affine singular guy. And this affine singular guy is supposed to be the same as the one given by intrinsic mirror symmetry. And this thing is a non-trivial statement that we don't need to prove this conjecture, but which will be nice to prove, and we plan to prove it in some later work. So actually, after this works, we are in some kind of ideal situation where our mirror, so we don't work with X bar, we work with this X. And this X is as nice as possible. It's like smooth. And X0 is some kind of like normal crossing divisor inside X. And then you can try to apply intrinsic mirror symmetry for X with this divisor X naught.
I'm a bit confused. Where is the Z from?
Yeah, so actually in all these arguments, I never work with Z. I always work with YD and this curve and this hypersurface C. So here we're on the mirror side. So it's yeah, that's right. So this Z kind of disappear. Instead of working with Z, I always work with Y, D, and C, which always contain the same, more or less the same information. From that, I can construct Z.
So Z is the mirror to X.
Yeah, that's right. Z is a mirror to X. So yeah, so here I'm on the mirror, so which is kind.
Exactly X?
No, they are mirror. They are mirror. So here it disappeared because I'm on the mirror side. So Z was related to YG, which was the original side. And now X is a mirror to Z. It's kind of a bad notation, but
So X is the mirror to Z is a prediction or?
yeah, that's it's a kind of prediction. And then, and this thing is you might want to test it. Like, can you prove enumerative geometry? Is it true that zero Gromov-Witten theory of X is captured by periods of CZ? This thing is a conjecture. And you can ask about homological. Is homological mirror symmetry true? And so you can test. And I think it has not been done because this setup has not been studied a lot. But so here we will kind of.
There's just technique, close free with the modulus.
Yes, that's right. And here, so here actually, so we'll give some non-trivial evidence. We'll claim that if you start with X and run intrinsic mirror symmetry, we'll actually go back. We'll actually find Y. Like we'll actually find Z. Or like actually we'll find the universal family of complex deformations of Z.
So in terms of intrinsic mirror symmetry, Z is the mirror to X.
Yeah, that's right. Definitely we prove that. Yeah, that's right. Starting from Z, we get some kind of combinatorial deformation theoretic definition of X, and then we'll prove that Z is the intrinsic mirror to X. And this thing is kind of where the kind of true difficulty is.
Is it obvious that X bar only have singularity at the origin?
No. So actually, X bar could also have some curves of singularities in dimension 3. And already in the toric situation, it might be the case. So, but we can prove that it has canonical singularities, in particular smooth in codimension 2, in codimension 1, and maybe in general it looks like that. But yeah, if you are in dimension 3 as here, what happens in this curve of singularity is like a curve of like actually in this setup it's just a curve of n singularities. So it's kind of easy. Like the difficulty is really at the origin where you get some kind of honest three-dimensional singularities, which does not come from like lower dimension. So how do we run intrinsic mirror symmetry? So before we had a fixed pair and the mirror should be affine. Here it's slightly different. We have some kind of degeneration situation. And the mirror is supposed to be this Y, which is like projective. So the correct thing to say is really, in some way, you can think it's really affine. If you think about the pair X, X0, actually we're not supposed to produce Y, but you're supposed to produce Y with an ample line bundle. So actually there is some affine variety, which is like a cone over Y. So the way it works in this setup, how do you run intrinsic mirror symmetry? You consider the dual complex of X0. So it's like X0 has finitely many components, so I get finitely many. So if I were in the toric situation, I will get back my kind of polytop, but here it's a kind of abstract polyhedral complex. And then I take the cone over that. And I have natural notion of integral points in this cone. And the intrinsic recipe tells us to consider an algebra which has now a basis element for each of these integral points in this cone. So I will have a theta p for every p in this cone. And this thing will leave over, now I consider all possible curve classes in X. So here the coefficients are seen on the form c beta 2t to the beta, where beta are like curve classes in X, like Novikov-like parameters for curves in X. And the claim is that, as I was summarizing in the other direction, intrinsic mirror symmetry gives you a way to define a product here. So there is again theta p, theta q equals some sum r, c, p, q, r. So before I had some ample line bundle on the original side, so I was producing a one parameter family. Here, it's like on the A side of X, I consider all possible Kähler parameters. So I will get a mirror which lives over like a big space parameterized by all possible curve classes. And okay, so in this setup, because X0 is so nice, X is smooth, X0 is normal crossing, you run intrinsic mirror symmetry, you get some associative algebra. And actually, this algebra is naturally graded because its integral points live in a cone, and so there's a natural height level. Like this original polytope is like height 1, and then there's a double, which is height 2, and so on. So this thing is graded, and so you can take the product of that. And I call that yx. And because the project, it naturally comes with a line bundle. There's a line bundle which is like O of 1 that I denote by Lx. And if everything makes sense, like if the mirror I created is really the mirror, if I do mirror symmetry again, I should recover the original thing. So we really expect this yx to be some kind of family of surfaces, deformation equivalent to the original y, and Lx to be a family of ample line bundle, deformation equivalent to the original line bundle L. So this thing is what you get from general intrinsic mirror symmetry. Actually, there's a few technical points. Actually, this X is non-compact. And if you read Gross and Zibert paper, they will assume that at least X, they will assume that at least X mapping to C, they will assume this map is proper, which is not the case. But that's okay, because every compact thing is contracted to a point under this map. So actually, all the curves you might ever care about live in a compact part of the space. So it's, at the end of the day, all fine. Some more serious issue is that what general intrinsic mirror symmetry will give you is a formal family. Because there will be some Novikov parameter, you sum over curve classes, you count curves, so you get power series T to the beta, where you sum over all possible curve classes. It's like you start on a large volume limit and you produce some kind of formal germ of the mirror around the large complex structure limit. And the basic question is, in general, the non-trivial question is, do these power series converge or what? So here there is a theorem that we prove in our paper, which is in this setup, if X is a Crepont resolution of a canonical singularity, if we started with something of dimension 2, actually this thing is not formal, but actually it's algebraic. Actually you don't get power series, but you get polynomials, finitely many terms. So this yx is actually defined over spec C any x. So maybe in complete generality you get some kind of formal family near some kind of large complex structure limit point, which is like a large volume point for your original guy. But here you get some honest algebraic family over a big, actually affine toric variety. So again, this is any of x because x is a memory dream space property. This thing is just polyhedral. So this thing is just a toric variety. And actually by construction, this toric variety is an affine patch on the toric variety we care about. So like the cone of curves is dual to the cone of divisors. So this toric variety is exactly some affine patch, or like affine chart, on this toric variety T. Okay? So it's one of the points of the intrinsic mirror symmetry construction. It produces some B model mirror over some base, which is a kind of A model moduli space by construction, because you count curves. And so T to the power of the curve class, like you count curves weighted by the volume or like surface according to the Keller form. So by construction, whatever you produce is living over the Keller moduli space by construction.
So why is this algebraic?
Sorry?
Why is this convergent?
So this thing is not obvious. So here is a, so definitely if you take a compact Calabi-Yau, it will definitely not be true. And Okay, so the rough idea is that this X is this a Crepont resolution of something affine. And okay. Roughly, the claim, okay, so it's kind of there's a projective morphism over some affine base. There's some relatively ample line bundle. And the claim is that if you fix the kind of like intersection of this curved class with this relatively ample line bundle, there will be finitely, for fixed P and Q, there will be finitely possibilities for R. And this thing is some kind of yeah, actually in some at the end of the day, some kind of tropical balancing type condition, saying like if you're in a toric variety, if you know the curve class, you know that the possible contact orders with the boundaries are kind of, like if you know all possible contact orders except one, maybe you know automatically the last one by some kind of balancing. Like maybe in tropical geometry, it would be interpreted as some balancing of some tropical curve. So there is some kind of analog of this balancing happening for some kind of tropical curve on this place here. But I don't think I can.
So why is that you find convergence?
Yeah, because it implies that in this product, like if I fix P and, okay, I claim that if I fix P and Q in C sum, there are finitely many R and finitely many beta.
So that follows on the
Something, so the balancing condition is coupled with some kind of control of the curve class coming from the existence of this kind of relatively ample line bundle. But yeah, I will not be able to say, yeah, to say more, I will need to actually recall the proof, which is definitely not obvious. In particular, the existence, we want a kind of relatively ample line bundle with nice properties. In general, I don't know how to guarantee the existence of that. I need to do some flops. After some flops, I can't find this line bundle. Yeah, so let's say it's not obvious. But the kind of moral, okay, if you really want to think about it, it's like Fano-like. So this thing you can contract to a point is like a Fano inside this canonical line bundle. Like it's like local model is like local P2. You contract P2 to a point. Or this collection of surfaces you contract, it has some Fano-like properties. And if you believe in the Fano situation, you get some kind of finiteness. There will be a similar finiteness in this situation. It's kind of the philosophically why it's the case. It's like if you can contract something, it's kind of positively curved. It's like Fano-like, and so you should have these kind of properties.
So do you need 2 dimensions in this thing?
Yeah, in this statement we need 2 dimensions for. Okay, maybe if you start with x0 with enough assumptions, probably actually the argument will work in any dimension. But maybe in general, first of all, I will not be able to construct x. And even if I were able to construct x, maybe the x will not have the properties needed for the argument. So it's safer to say we do it in dimension 2.
Okay, the question is, if you can construct x and also can construct y, and y being algebraic.
Yeah, that's right. Yeah.
Do not be two-dimensional.
Yeah, that's right. So this thing is definitely a hard part. Like, if you run interesting mirror symmetry in general, you get a formal thing, but actually it's not formal, but it's algebraic. And this thing is really affine patch of the toric variety we care about. So the toric variety we care about, here is a picture of the toric variety. And there is a various dimensional, 0-dimensional strata corresponding to the various Keller cones in this fund, which correspond to the various Crepont resolutions. And here what we did is we picked one Crepont resolution, and then we proved that the intrinsic mirror family is actually an algebraic family on some kind of on the affine chart around this torus fixed point. Yeah, that's right. Yeah. And so another thing which is very non-trivial is a claim that this thing glue. If you take different Crepont resolutions, you create is like taking different large volume limit on the side of X. So you create different, you get intrinsic mirror families on different charts of this toric variety. And the claim is that they are compatible on the intersection. And this thing is not obvious because in one case you use count curve in X, and here you do count curve in some X prime. And X and X prime are not the same. So here we use the fact, so here we essentially use again dimension 2. It's known that there is a classification of flops which can appear. So in general dimension, flops can be, we have no idea what a general flop is. But here in dimension 3, you have a perfectly understanding of what the flops are. At the end, they are all like ATIA flops. P1 with normal bundle -1 gets contracted and is resolved. They are kind of all like that, we can prove. And then it's enough to control what happens to this intrinsic mirror construction along this simple flop. And this flop is like simple enough so that we can follow what happens to our curve count. And so we can get this gluing. Okay, but this thing is also another part of the work. So at the end of the day, you get, once you glue, you get some global family over the toric variety you care about with some line bundle. I did not explain how to get a divisor D, but I claim there is a natural way to get a divisor D. And I should explain how to find a curve C, like in dimension 2, it is a curve. So by construction, our line bundle L comes with a canonical basis given by this theta function. So it is where I was claiming at the beginning, that for the conjecture to be true, this line bundle should have a canonical basis, but in this construction, whatever we produce is a line bundle coming with a canonical basis. So, and I can look at the curve with equation is the sum of these theta functions. So the section of L, they are like the points at height 1, there are finitely many of them, there are finitely many theta functions. I look at the equation sum of theta function equal to 0. This thing is one element, this thing is a section, so this thing is a curve. And the kind of hardest part of the story is a claim. So here I've produced
What is the sum of this what is particular choice?
Yeah, so the claim is that what will give the right answer. For example, in the toric situation, if you keep correctly track of the curve classes and so on, it kind of recovers a kind of universal family. So the thing which is the least obvious is that so we've produced a family of something, and we can argue that this Y is a family of surfaces. D is divisors. And the last thing is that this thing is a family of KSBA stable, which means that if I define C that way, then the corresponding curve always avoid the zero-dimensional strata of D. And this thing should happen everywhere. So inside the moduli space, we can prove the surface will be irreducible, but at the boundary of the moduli space, the surface will break into pieces. And then we need to prove that this curve, which also breaks, also never hit any zero-dimensional stratum. And this thing is the hardest part of the story. It's like proving that this kind of canonical basis has a kind of the same property as the monomials in toric geometry. That if you consider an equation with coefficient are non-zero, you don't pass through the zero-dimensional strata. And this thing I will not have time to explain. I'm already over time. So it's the hardest part, and it uses in an essential way an understanding. There is some kind of very big induction, because at the boundary of the moduli space, the thing breaks into pieces. And you really need to understand in details how this breaking on the B side is mirrored to some birational operation on the A side. Like there is some, if you have some X is kind of mirrored to the general guy here, with a kind of intermediate, like partial Crépin resolution correspond to like various kind of degenerations. And you need to understand, like, so the mirror is constructed involving curves here. And if there's something partial, there will be curves which are contracted here and curves which are contracted here. And you can match that to some kind of description of what happens at the boundary of the moduli space. So you really need to match the kind of birational geometry on the A side, like mirror construction involves curve counting, so you need to understand how this curve counting is affected by these birational transformations to match it to a property of the mirror you construct. Okay. So anyway, at the end of the day, you prove that, and once you prove that, you get a map to the moduli space.
So you need to have some property or some computation of the number? Or?
Yeah, so I think at the end, we never need to, okay, in general, these numbers are definitely an example where they're arbitrarily complicated.
Yeah.
So definitely we cannot, okay, we can explain, there is a scattering diagrams calculating this number, which essentially live in this picture. There is some initial ways here. So here you could draw a scattering diagram, explicit, which can be arbitrarily complicated. And yeah, so at the end of the day, we just use the kind of geometric properties. The key point is that they count curve inside this geometry. So there will be some, and so in this geometry, some curve will get contracted, some curve will not, and stuff like that, yeah. So at the end of the day, you get a map from your toric variety to your moduli space. And you need to prove that whatever family you constructed is not a constant family. It will be unlucky. So you need to prove that this thing is really kind of universal. Like, and I will also stop that. So you can prove it's essentially injective, like it's finite. And surjectivity is just a dimension calculation. It happens that this thing has a right dimension, and it's known our thing is irreducible, and so we get what we want. Okay, I will stop there. I'm already over time. That's it. Yeah.
Okay. Is there any questions? Yes.
Yeah, so you defined, you constructed Y.
Mm-hmm.
What's that?
Yeah, but once you have Y, D, and C, you can reconstruct Z.
Of course,
yeah.
absolutely. My question is the following. Your Y is algebraic.
Yes, if
Now-
you're in algebraic family.
Now, if I just look at the local mirror symmetry paper, there Z will not be algebraic, right? Is that correct? Like like the example, there'll be corrections like UV equals.
Okay, so let me say I do not understand these corrections.
Yeah.
So it's like the usual mirror map picture. Maybe I never understood. Maybe I will understand one day. But it does not appear in this story. In the way we appear, we directly get. It's related to the fact we don't try to match or to figure out what mirror maps are and so on. So I think
But I'm just.
That's so for example, this map has some enumerative interpretation, and I don't know how it's related to whatever we do here. This is a good question, but I don't know it.
Fantastic. And then my second question was, I think you promised you were going to say something about epsilon equals 0.
No, I did not.
Okay. So you promised you're going to say something about maybe just Y, D?
No, I'm not saying. Yeah, that's right. So let me see.
Meaning the fiber, the general fiber on one side versus
just Y, D. Yeah, so definitely there is some kind of map, at least on the interior of the moduli space. You could just forget the C, and you just have some kind of map to the moduli. So the problem is that I don't know a canonical compactification of the moduli space of YD. Just the local RBO itself without any extra data. I don't know how to compactify it. But yeah, but it's known that this thing is some kind of torus. Because in dimension 2, all of these things are obtained from something toric by doing some blow up. The modular is just the position of the points you blow up, and so at the end of the day, some kind of big C star, maybe up to some finite group. And this C star is kind of compatible with the C star we produce here. So here there is a kind of big C star, which is related to the fact you can move the curve and you can move YD. And this C star is kind of compatible with some kind of obvious C star just coming from moving YD. So this thing is something which does not exist in the toric situation, or which is trivial in the toric situation. It's just a point. And everything happens because you can move C, but here you can move both C and YD. So indeed, there is this kind of two direction in the moduli space.
so cool. Yeah, very.